Okay, so today I would like to continue our observational overview of active galactic nuclei. And today we will be talking about the narrow line region, which I will abbreviate as NLR. And a reasonable subtitle for this talk would be a discussion of the environmental effects of AGNs upon the galaxies in which they live. So let's start with some overall context. You will remember our AGN powers of 10. We have talked quite a bit already about the black hole region on very small scales. We've said a little bit about the accretion disk. We've also talked about the broadline region. We've talked about outflowing winds, which in fact span a broad range of scales, as was discussed in the previous lecture. And today, we are going to focus on the narrow line region, which starts further out in general, may start out around a light year or even somewhat further away from the active nucleus, and then extends out much further still, extends out to the 10 parsec scale, the 100 parsec scale. Here you can see narrow line clouds indicated. And then in fact, if you look at the extended narrow line region, that can extend out to kiloparsec scales, out to scales of a parsec, shown in this panel, or even 10 kiloparsecs shown in this panel. So this can be a very large structure where the extended narrow line region can extend out to essentially the size of an entire galaxy almost. Okay, so let's review the distinction between broad lines and narrow lines. We talked about the broad lines extensively in the lecture on the broad line region. We are now going to be focusing on the narrow lines, which we have not given very much attention so far. So the narrow lines, first of all, well, they're narrower. They have Doppler widths typically less than about 900 kilometers per second, where for comparison, the broad lines have Doppler widths of like 1,000 up to 25,000 kilometers per second. And you can see that distinction in this spectrum. Here, for example, you can see the very different profile of the forbidden O3 lines here compared to H beta and H alpha and so on. Another key point is that unlike the broad lines, which vary on short time scales of order days, the narrow lines do not vary on short time scales. Furthermore, the narrow lines are believed to arise in relatively low density gas with a typical density of order 10 to the 3 particles per cubic centimeter, although there's a fairly broad range for that density, as we will talk about, whereas, again, the broad lines arise in considerably denser gas, and then, again, the narrow lines are thought to arise in this narrow line region. So again, here is your example of the sort of H beta, O3, H alpha region. O3 is a very prominent narrow line region line, but then also note that there is this spike here sitting up on H beta. So H beta has a narrow line component to it sitting atop perhaps the broad component of H beta there, and similarly for H alpha. So the recombination lines also have a narrow component to them quite frequently. And this plot here shows for a type 1 quasar template some of the strong forbidden NLR lines, which I have marked here with these red dots. And so here is, again, the O3 lines. You can see their profiles are substantially narrower than, for example, H beta. Here is H alpha, which is blended with forbidden nitrogen 2. There are also other lines like oxygen 1 here, sulfur 2 here, and so on, neon 5 here. These are some of the strongest forbidden NLR lines. A particularly nice way to, in fact, focus in on just the NLR lines is to consider the orientation-based unification model, which again, I have not discussed in much detail yet. That will be the focus of next week's lecture. But one point I will just make for now is that unlike the broadline region, which is thought to be made on quite small scales and thus is interior to the torus, the narrow line narrow line region or NLR emission is primarily formed exterior to the torus. And so sometimes you will have systems that are obscured, say that the safer 2 orientation here, where the small scale continuum from the nuclear region and the broad line region lines are blocked, and all you see are the narrow line region lines. And here is a nice example showing precisely that. So in this case, you are utilizing this obscuring material to providentially block the nuclear continuum and the BLR lines. The NLR lines are dominant throughout the spectrum, and you can see them very prominently here. Here are the oxygen 3 lines. They're also plotted there. Notice the strong oxygen 1 here, and the various other NLR lines here stand out quite prominently. So these lines can be very apparent when you look at obscured systems, because again, the narrow line region is considerably larger than the torus, and so it is not blocked when the torus lies along the line of sight. Okay, so now let's lay out some basic properties of what we think the narrow line region is like, and I will give you, of course, the observational evidence for why we think these things. First of all, the narrow line region represents the largest spatial scale where ionizing radiation from the AGN dominates. And so as we will see, this is a system where the kinematics generally are not dominated by the supermassive black hole, but where the ionization is. So again, the narrow line region is being ionized primarily by photoionization from the AGN. For nearby AGNs, the narrow line region can often be spatially resolved, and it has a size of 200 plus parsecs, even in local safer galaxies, and can be even larger in quasars. And in fact, here is a nice plot that illustrates that. This plot shows, as a function of O3 luminosity, the characteristic size, and this is a logarithmic scale here in parsecs, for the forbidden O3 emission. Now, you have to be a little careful in defining what you mean by that, because there are different methods of measuring the O3 emission. High sensitivity methods, such as IFU mapping and long slit spectra, give a relation up here, whereas lower sensitivity methods, such as HST narrowband imaging, well, they don't detect the full extent because they have lower sensitivity by often an order of magnitude or more. They give a relation more like this. So this is perhaps a high sensitivity relation shown with the dark symbols. And you can see that the narrow line region is very large. It starts with sizes of, again, several hundred parsecs. And then as you go up in O3 luminosity, can become very large indeed, reaching up to like 10 kiloparsecs. So this can be a very large structure when you go up to high luminosity systems, as we will discuss. Okay, so that's the characteristic size. And well, then, in such physically large systems, we have the great advantage that we can map out directly the physical and kinematic properties spatially across the narrow line region. Here is a classic example of doing exactly that. This is the famous local safer galaxy NGC 1068. In this case, we believe the nucleus is down here, and this large plume here, which is about 200 parsecs long, represents the narrow line region. And this is showing primarily the O3 emission here from the narrow line region. You can see, first of all, that the line emission here, this line emission region, is clumpy and complex. You can see it has this complex character. There's sort of filamentary structures, there's blobs throughout it, and so it's a clumpy, complex structure, to be sure. It usually is not spherically symmetric, although there are some counterexamples there, but it usually is not spherically symmetric, but it often is roughly axisymmetric. That is, you can define an axis running along like this, and at least a first approximation, narrow line regions often appear to be roughly axisymmetric along an axis like that. And in fact, that axis generally coincides with the radio axis in cases where extended linear radio emission is detected in these systems. So normally the NLR axis and the radio axis line up pretty well. I'll say more about that a little bit later. And then furthermore, in some sources, We also see strong line emission from regions where the radio jet is colliding with the interstellar medium, perhaps causing shocks, and that may be an additional source of ionization, of course, secondary to the photoionization from the nucleus, but may also be acting. Okay, so then, if you look at just the full width half maximum values of NLR lines, they are typically between about 200 and 900 kilometers per second, with the line profiles varying spatially as you go across the narrow line region. And I'll show you some nice examples of that in a few slides. We see a wide range of ionization states from the narrow line region, including low ionization lines like the oxygen 1 at 6,300 angstroms that I showed you in that previous slide. And then, of course, also these high ionization transitions like oxygen 3, which I also pointed out. And then sometimes we see even very highly ionized species, such as the iron coronal lines, also from the narrow line region. So if you look at the line ratios, you make measurements of all the lines. Well, we infer, as I've already mentioned, that the narrow line region is mostly a photoionized medium. The nuclear radiation is shining out from the AGN upon the narrow line region, and that is what is making the narrow line region ionized. Okay, there may be some possible additional ionization by shocks from radio jets. That is still a bit of a debated issue, the details of that, but I don't think anyone would argue would argue against the idea that the primary ionization mechanism of the narrow line region is photoionization by the AGN. Okay, then if you look at the sort of density, and you ask what can we say about the density of the narrow line region, well, it has to be sufficiently low to allow forbidden transitions. And in fact, the density is thought to vary between about 10 to the 2 and 10 to the 6 particles per cubic centimeter across the narrow line region. And I'm going to show you now a rather busy plot that has a lot of very useful information on it in sort of summarizing many of the essentials of the narrow line region. So again, this is a rather busy plot, but it shows as a function of luminosity, okay, along this axis in parsecs, it shows the expected line luminosity for various lines from the narrow line region. And these have been worked out under a particular set of reasonable ideas of what people think the narrow line region is like in terms of its covering factor, in terms of its metallicity, in terms of the shape of the ionizing continuum, and then considering also the method by which the gas is confined. And you can read about all the assumptions and so on in this paper. They're quite reasonable assumptions, I would say. And so then you can look in each one of these panels, and for example, in this panel, you see many of the longer wavelength optical forbidden lines. Okay, and some further ones at shorter wavelengths are shown in this panel. And then down here in this panel are a bunch of infrared forbidden lines. And these turn out to be very important tools for probing the narrow line region, as I will talk about soon, these infrared lines. And then in this panel, it also shows emission from recombination lines. It shows X-rays. It shows the total gas emission and the total dust emission. And we'll talk more about that soon. But the point I want to highlight now is that, again, the density has to be quite low to allow these forbidden transitions. In fact, the density is labeled up here in particles per cubic centimeter. And for each one of these curves, there is this little vertical hatch running along it. And that is the critical density for one of these lines. And essentially, for densities above that critical density, you can see the luminosity from that particular line drops off rapidly here, 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 and so on. And of course, that's due to collisional suppression of the forbidden lines when the density gets too high. Okay, so the point I want to highlight here is the densities where you can start to get substantial line luminosity from these forbidden lines, again, starts around 10 to the 6 particles per cubic centimeter, and then it extends down to 100 or even less particles per cubic centimeter. So that's the typical range over which we think much of the narrow line region emission is able to be produced. And that holds for this particular panel. It also holds pretty well, you can see, for this panel and similarly for this panel. Okay, so those are the sort of typical densities people are considering when thinking of the narrow line region. And just for reference, to give you a sense, remember we talked about the broad line region in a previous lecture, and as a sort of characteristic ballpark number at this particular luminosity, the broad line region would have a size of about 0.03 parsec, so on a much smaller scale than anything being shown here. So that shows you the characteristic size, the characteristic emission as a function of radius, and also the characteristic densities people are thinking about when they attempt to model the narrow line region. Okay, so then, if you look at the observed line ratios and do photoionization modeling, you can infer temperatures of the gas in the narrow line region. It's between about 10,000 and 25,000 Kelvin, again, varying across the narrow line region spatially. And this is a very important point. At the distance of the narrow line region from the nucleus, from the center, dust can survive. The intensity of ionizing radiation has dropped off sufficiently, and the gas is sufficiently cool that it doesn't sputter dust. And so dust is able to survive in the narrow line region and cause self-extinction. Okay, so back here, when I highlighted this sort of complex, clumpy, patchy appearance to the narrow line region, a lot of that is almost surely arising due to dust being present in the narrow line region and causing internal extinction of the emission from the narrow line region. Now, that immediately tells you that if you want to be able to study the full body of the narrow line region reliably, you're probably going to be best off going to longer wavelengths where dust has a reduced effect. And so that has in fact motivated extensive studies over the past couple of decades of the narrow line region using near infrared lines. And you can see again in this panel, this lower left panel here, many long wavelength near infrared lines are highlighted here. And again, an important reason for that is they can cut through a lot of the obscuring dust and allow you to study the full body of the narrow line region, mitigating dust effects. Okay, and then further, a couple of other points that come out of modeling of the narrow line region. If you look at the estimated total mass of the photoionized gas in the narrow line region for safer galaxies, it's like 1 million solar masses. Now, of course, that doesn't mean the entire all the gas that's out at these radii only has a mass of about 1 million solar masses. Here again, we're just speaking of the photoionized gas that's responsible actively for producing the NLR emission, which is likely only a thin layer of much more massive molecular gas clouds in general. Okay. Remarkably, however, and I want to point this out, the emission line strengths from the narrow line region, even though they're coming from, again, of order 1 million solar masses worth of gas, are often comparable to those from the broad line region. And you will remember that the broad line region is thought to be made by orders of magnitude less gas than this. The broadline region may come from 10 or 100 solar masses of gas. Again, that's the photoionized gas actively emitting. And the reason why the broadline region is able to compete with much less mass compared to the narrow line region is because the emissivity of the gas in the narrow line region is much less. That generally scales as the density squared. And again, as I mentioned, in the narrow line region, the emission is often dust suppressed, and so that leads to a much lower emissivity of the gas in the narrow line region than the broad line region, and allows the broad line region with, again, much less gas to produce lines of comparable strength. Okay, to highlight a little bit more the importance of this dust, in this lower right panel here, in fact, they also very helpfully show the total gas emission from the narrow line region. And this is scaled down by a factor of 100, so it fits on the plot. And then also here is the total dust emission. And you can see the total dust emission dominates all the emission from the gas. And that just highlights how important the role of dust is in absorbing radiation from the nucleus in the narrow line region and then re-radiating it. The dust is in fact the dominant radiation source out at these distances. Okay, So a couple of other points. Observationally, people have, for a few relatively well-studied nearby systems, had found that over a long span of time, the narrow line region lines do vary. Now remember, I told you the narrow line regions don't vary rapidly like the broad line region. That is certainly true. But they do vary over long time scales. Here is detailed monitoring of the local safe-work galaxy NGC 5548, in this case spanning around 2 decades. And you can see the intensity of the forbidden O3 emission is slowly declining over the years, indicating that some of the narrow line region emission is fairly compact, with a size scale perhaps of order 1 to 3 parsecs or so. Okay, so much of the narrow line region emission is on fairly small scales, and it is observed directly to vary, which is a useful constraint just on the innermost size of the narrow line region. Okay. Another important thing to highlight is the luminosity dependence of the narrow line region. Just like for the broad line region, the narrow line region line equivalent widths drop with increasing continuum luminosity. Okay, such that in high luminosity quasars, the narrow line region lines can sometimes be undetectable or nearly so. And here is a plot that's quite useful in this respect. I showed you this plot previously when we talked about the Baldwin effect for the broadline region. And again, you can see here for the H beta O3 region and extending out to magnesium 2 here, you can see that as you dial up the luminosity of active galaxies, here spanning around 5 orders of magnitude in luminosity, well, you can see the equivalent widths of the broad lines and also the narrow lines drop as you go to high luminosities. You can see the equivalent widths up here at very high luminosities are much, much reduced compared to the lower luminosity systems here. And indeed, for the narrow lines specifically, well, for O3, for example, it in fact drops more strongly with luminosity than does, say, the broad component of H alpha. And that's what's shown here. You can see as you dial up the luminosity of broad H alpha, which is a reasonable bolometric luminosity indicator for a system, well, the ratio of the O3 luminosity compared to broad H alpha drops. And so the point here is that as you dial up a quasar's or an AGN's luminosity, the narrow lines often decline faster than the broad lines do. And you can even see that here. You can see, look at the narrow lines taking this enormous hit going from this upper spectrum all the way to this lower spectrum. And H beta declines strongly as well, but not as strongly as does oxygen 3, which declines quite strongly indeed. Okay. So the narrow line region lines drop with increasing luminosity, just like the broad line region lines. Why is that? Well, the first suspect there, of course, is that we know the spectral energy distribution of active galaxies changes with luminosity. We talked about that when we talked in the lecture about the black hole region, for example. And the SED changes generally becoming softer as you go to higher luminosity. That dependence upon luminosity and or perhaps the Eddington ratio likely contribute to the drop in the intensity of many of the narrow line region lines. O3, for example, being a high ionization line, suffers surely on account of this. But that probably does not fully explain the results when people consider this in detail. And so what else is going on? Well, we don't know for sure. Perhaps more luminous AGNs become effective at substantially evacuating or destroying gas in the interstellar medium, and thus, owing to those effects, leaves less large-scale diffuse gas present for continued emission from a narrow line region. So the gas that might have formed the narrow line region, once you dial up the AGN luminosity to become sufficiently large, or alternatively dial up the Eddington ratio to become sufficiently large, you may actually evacuate a lot of the gas present that otherwise would have been there producing much of the NLR emission. So the system may tend to evacuate itself. That's a reasonable possibility. Another point which I want to highlight, however, is that here we've talked about the luminosity dependence, but even at a roughly fixed continuum luminosity, there is a wide range of NLR line strength. You can see that with this plot, for example, which again, you can see there's a very large scatter in this relation. And much of that is due to a wide range in NLR line strengths, even at a fixed continuum luminosity. And in fact, you can see that just graphically in this set of spectra that come from that important paper by Borison and Green studying the PG quasars. And what I've done here is I've marked with red dots, just 3 examples. And there's other ones that are available on these plots if you look at them in detail. But look at these ones with the red dots. Here you have systems that have very strong, large equivalent with forbidden O3 emission. There, and there. See the extremely strong, large equivalent with forbidden O3 emission there. And in panels like this one, for example, focus on the middle spectrum, which has subtracted out the iron 2 emission to give you a cleaner spectrum to look at. You can read the details in this paper. And then, by contrast, I've marked with blue dots other systems that have much weaker, much lower equivalent with O3 emission. Here, for example, is one of my favorite quasars. I've had a lot of fun with this quasar. And you can see the O3 emission is much less prominent than this system here, for example. And similarly here, look at this system here. The O3 emission is very weak indeed in this system. Okay, and similarly here, this is another one of my favorite quasars here, 2112, and you can see the O3 emission is very weak there. And so the point is, again, even at a roughly fixed luminosity, there's a wide range of O3 strengths. This relates to that eigenvector 1, which I will speak about more a little bit later today. And this may be due to the covering factor of the illuminated NLR gas changing with the Eddington ratio. You may tend to focus the radiation more intensively at high Eddington ratios, leading to a decline in the NLR line strengths. Okay, and again, I'll say some more about that later on. Okay, so those are some basic points about the narrow line region. Now I want to say some more about the kinematic insights people have come up with by studying the narrow line region. They've been doing these types of studies for many years. There are many fascinating things that have been found. I'm just going to give you a few highlights of what people have found investigating the kinematics of the narrow line region. Okay, first of all, people have for many years, this is some nice work from 1991, have looked at just the integrated line profiles from the narrow line region. And here are for one active galaxy, Markarian 766. They show the NLR profiles from H beta, O3, the other O3, H alpha, nitrogen 2, sulfur 2, and so on. And there's a couple of points that are worth noting. First of all, the NLR line profiles are non-Gaussian. You can see these profiles would not be well fit by a Gaussian. They have stronger bases than a Gaussian. Okay. And another point that's worth noting is, especially if you look at the line base, these profiles are often blueward asymmetric. And you can see that here. These profiles have a strong blue sort of tail to them, which is much less pronounced over here on the red side. You can see that here and there, for example, especially clearly. Okay, that basic asymmetry of the integrated line profiles is thought to arise from some combination of outflow motion and dust extinction. Okay, so people have suspected for a long time, and now we have very compelling evidence of this, as I will show, that the narrow line region is often in a state of outflow. Okay, and again, when you have an outflow, well, the blue side of the outflow is the side that's closer to you, and thus is the side that is less prone to dust extinction, whereas the side that would be redshifted is more prone to extinction, and that's what leads to the line asymmetry. So again, this is the side that's closer to us, that is coming toward us. It's less extincted. This side over here is more heavily extincted, and that leads to the blueward asymmetric line profiles. At least a first approximation. That's what people think is largely causing this basic effect. And as we will see, this basic phenomenon is also seen directly in NLR line mapping, as I will show you. Furthermore, in a given object, the NLR line widths are generally larger for high ionization species, just like what we saw for the broadline region. In other words, there is evidence for radial stratification of the narrow line region, exactly like you might expect from photoionization, and exactly as is seen for the broadline region. The same thing essentially holds, at least a first approximation, for the narrow line region as well. Radial stratification according to ionization level. Other important work from the early days is that, well, you can look at the narrow line region line widths and see how they correlate with the host galaxy bulge luminosity. And they clearly do correlate with it. And you can see here a nice example of that. This again shows that the bulge luminosity, which is telling you essentially what the bulge gravitational potential is like, versus the O3 full width half maximum. And while there's a fair amount of scatter here, you can see that in general, as you go to broader line widths, okay, you are dealing with bulges that are progressively more luminous, more massive. Okay, this indicates that the NLR widths are indeed substantially variable in origin, okay, but that they reflect the gravitational field of the stars in the bulge here, and not so much the gravitational influence of the black hole itself. This is quite plausible. You will remember, here's our AGN powers of 10 plots. Note there are many stars interior to and coinciding with the narrow line region. Remember in these nice plots made by Pat Hall again, many of these, well, all of these little gray dots, are representing the possible, where a star would lie on average. We don't think they're, of course, arranged in a grid, but that's sort of the characteristic density of stars being shown. The point being now that once you get out to these sorts of radii, there are many stars interior to the narrow line region expected. And that, of course, if you go out to even larger radii, this again goes out to about 2 light years, 1.5 light years or so for a 10 to the 9 solar mass black hole. But if you go out to 10 parsecs, now you have the entire stellar cusp and the stellar core lying interior to much of the narrow line region, which could lie out at 100 parsec scales, as shown here. Okay, so again, we fully expect there, and we know just from direct imaging, that many stars lie interior to and coincident with the narrow line region, making it quite plausible that, again, the narrow line region widths are virial, but reflect the gravitational field of the stars instead of the black hole. Okay, another important result that comes from looking at plots of this type is that AGNs with powerful radio jets lie off the correlation, having larger widths than one would expect. And that's what's shown here. Here they nicely plot the systems that have linear radio structure and high radio luminosities here with pluses. And you can see all the pluses here in general systematically lie toward higher full width half maximums than systems that are radio quiet or have lower power radio emission. So in other words, you get a broader line profile at a given fixed bulge luminosity for the systems that have powerful radio jets. That is taken to be evidence that apparently there can be also be some non-virial component to the velocities, such that, for example, interactions between powerful radio jets and NLR gas may cause additional motions of the narrow line region in some cases. Just this is pretty good statistical evidence that something like that is probably going on. Okay, so remember I talked about how people have made much further advance by now doing spatially resolved measurements of the kinematics of the narrow line region. Here's one nice example from this paper by Muller-Sanchez et al. And in this case, they have used silicon-6 forbidden emission, which is one of these near-infrared lines, which remember I told you were very important for penetrating through all the dust that is present in the narrow line region. And so by going out to a line like this, you minimize extinction effects And furthermore, they have used measurement techniques here that allow them to obtain very high resolution imaging. Note the offsets here are less than an arc second. So this is very impressively high resolution imaging. And they can go and do spatially resolved spectroscopy. The spectrum over here looks like this. The spectrum over there looks like that. The one over there looks like that, and so on, as shown here. And well, you can see that spatially, the narrow line region, the line profiles from the narrow line region vary substantially. This profile is very different from this one, is very different from this one, is very different from that one, and so on. So there is complex, spatially resolved kinematic changes across the narrow line region. And one must always bear that in mind. And furthermore, if you're working in the optical, must bear in mind the fact that there are strong extinction effects present as well when one looks at just an integrated profile of an entire NLR line. There's a lot of internal complexity to the line that is spatially resolved and also being affected by dust. Now, this work has been extended, and they have in fact made beautiful flux and velocity maps, in this case using bracket gamma, which is at about 2.16 microns. So again, minimizes the extinction effects due to internal dust in the narrow line region. And so for each one of these panels, well, you see they have a given active galaxy. Here it's NGC 2992, and here's NGC 3783, and so on. And well, you can see you have a flux image over here, and then you have a velocity map derived again from Doppler shifts of bracket gamma. And here's another system, here's another system, here's another system, here's another one, and there's more in the paper. And well, you can see a number of remarkable things. In the velocity maps, you can see that oftentimes you have one side of the NLR emission that is, again, as measured in bracket gamma, that is blue shifted, and the other side that is red shifted. And you see, again, the same type of thing here. You see some red emission here, more blue emission over on this side. Here, again, red is over here, blue is over there. Here, this is another quite clear case where you have, again, red shifted, blue shifted, indicating that you're seeing some kind of a biconical outflow behavior of the emission from the narrow line regions. These things often have sort of biconical outflow structures to them. Again, these are local Seyfert galaxies. If you go up to even more luminous systems, people have also now done detailed measurements of here O3 emission around sort of luminous obscured quasars at redshifts of about a half. And here you can see these very large O3 nebulae that are seen. And for scale, this bar represents 10 kiloparsecs consistently across all these images. And look at these impressive O3 nebulae that people see around obscured quasars. And again, people can also then go in and do kinematic measurements of these, and you often see, again, characteristic redshift, blue shift patterns, redshift, blue shift patterns here as well, and so on, indicating, again, that you have some sort of biconical type or some sort of an outflow that's red shifted on one side, blue shifted on the other in these systems. So, you know, this is the type of detailed, spatially resolved kinematic mapping people can now do for these narrow line regions. People also then have gone and looked at higher luminosity objects. Here is an interesting study of extremely red quasars, in this case at redshifts of about 2.5. So these are very luminous quasars now. And in some cases, you see extreme outflows as traced by forbidden O3. And you can see that here. These are basically best fit profiles of oxygen 3. The technical details of how exactly they're fit are complex, but are described in this paper. And you can see that in many cases here, you see very broad O3 emission. Note here that's minus 5,000 to plus 5,000 kilometers per second, where I believe blue shift is over in the positive direction in this particular plot. And so you often see blue shifted and very broad in terms of full width half maximum, spanning thousands of kilometers per second O3 emission. So here, in these particular extremely red quasars, you have O3 emission that appears as broad as what we often measure for BLR lines. And because, again, you're dealing with forbidden O3, which is, again, a forbidden transition that can only be made on large scales, this is indicating that, and this is supported by photoionization modeling reported in this paper, in fact, that the O3 emission here is likely extended on kiloparsec scales in these luminous quasars, indicating that you may indeed have outflow on galaxy size scales that is capable of causing feedback in these luminous, extremely red quasars. Okay, so those are some examples of the types of things you can do by studying the kinematics of the narrow line. Fascinating results are indeed found. Okay, now I want to move on and talk about ionization cones and the so-called extended narrow line region. So, people often see so-called ionization cones in maps of high excitation lines. These are wedge-shaped structures of gas that are being ionized by the AGN continuum, and they often begin in the classical narrow line region and extend outward, reaching kiloparsec scales, thereby forming this extended NLR. Okay, and it's best just to show you a few examples to appreciate what I'm talking about here. So here is the nice example of the Circinus galaxy. This is a nearby, very well-studied active galaxy. It's an obscured system. And here you can see this amazing cone of ionized gas, in this case measured with this particular line ratio, which shows the ionization of the cone, sticking up out of the Circinus galaxy. And these contours here show the characteristic scale of the galaxy. So this structure is very large indeed. Here it is shown just here in this specific O3 line here. Okay, and well, that's an example of a impressive ionization cone. Here's another example. This is NGC 5252. Here's the galaxy continuum. Here is O3 emission, showing the impressive ionization cone in this particular object. Here's another nice example of a nice ionization cone here being traced in Passion Beta and in Forbidden Iron 2 here. So again, you can see these impressive ionization cones in many of these active galaxies. Now what's going on there? Well, we're not exactly sure, but the typical thinking, okay, is that the fairly sharp edges of these ionization cones are being defined by the collimation of light from the active nucleus. And so here is a typical idea. So here you have an accreting supermassive black hole. You have a toroidal structure, and that could be the obscuring torus of the unified model, as we will discuss more soon. And that torus will block radiation, ionizing radiation, from getting out in highly equatorial directions. And so you naturally will collimate the ionizing radiation into a cone-like structure that shines out into the galaxy and thereby could produce one of these ionization cones. That's the standard thinking, is the torus of the unified model may be producing the ionization cones. That's the collimator that collimates the radiation that causes the observed ionization cone structure to be made. So again, that collimation could be due to shadowing by the torus. That is often taken as the standard idea. Or alternatively, you could have an inherently anisotropic ionizing continuum otherwise, if there was some other source of shadowing, perhaps a thick accretion disk, a geometrically thick accretion disk on small scales. That could also collimate the ionizing continuum. But again, the standard idea is the torus of the unified model is likely the collimator here. Another point to make is that these ionization cones come in both single-sided and biconical types. Here you have a single-sided type. Here you have a clear biconical type. Okay, that single-sided or biconical morphology, well, the idea there is that the single-sided ones presumably have an obscured counterpart on the other side that you're not seeing very easily due to the obscuration. Okay, now people have studied these ionization cones extensively, and they have arrived at a number of fascinating conclusions about them, especially by looking at them in kind of a statistical manner. So here is a table with a lot of numbers in it. I'm not going to try to go through every single number, but what I want to point out here is that people have looked at, for example, the position angle of a linear radio source. You can often, even in these safer galaxies, even the radio quiet ones, you can see often a linear radio source, a small scale jet perhaps, in these systems. And then you can also measure the corresponding position angle of the ionization cone. And they often are rather similar. Here you can see, 33 plus or minus 2 compared to 32 plus or minus 5, or 57 plus or minus 5 compared to 60 plus or minus 5, or 345 plus or minus 3 compared to 345 plus or minus 3, and so on, looking through the table. 307 versus 304, 270 versus 262, 308 versus 300, and so on. So there's a remarkable degree of alignment between the ionization cone and the radio axes, which is quite interesting. That's telling you that the collimator of the jets and the collimator of the ionization cones are well aligned. You can just statistically see that from looking at the position angles and how they correspond to each other. And that's quite interesting because, according to our current understanding, we believe that the radio jets are often formed on very small physical scales. Here again is our powers of 10 plots where I've pulled out the two relevant panels. In fact, in M87, for example, people can now directly image the jet and see a linear jet forming down at 20 gravitational radii. You can see this paper for some of the nice details. So on a very small scale, we can see that the radio jet is collimated. The direction for the radio jet is being set down there at very small scales. Whereas, by contrast, you have to go up to the next sort of power of 10 diagram to get to the obscuring torus, which is thought to be the collimator of the ionization cones. That may be a structure that is on a scale of sort of 40 times larger than the collimation scale of the jet. Yet this structure and the torus structure are thought to be generally co-aligned pretty darn well, such that the position angle of the radio source and the position angle of the ionization cone align well. So that tells you that there's an underlying, structure to these systems, and once you pick your preferred direction, the system maintains a preferred direction pretty often, running all the way from very small scales where the radio jet is being launched, presumably, to the scales where the ionization cone is being made, which again is generally thought to be the obscuring torus. So these systems are lined up. There's internal alignment of them that is enforced remarkably well, given how complicated and messy these systems surely have to be. There's an underlying structure there that seems to be enforced pretty well, just empirically. Also interesting, there is no clear relation between the ionization cones and the overall orientation of galaxy disks. So in other words, there's no reason to think that just because a galaxy has an alignment a particular way, the supermassive black hole is going to be orbiting and the accretion disk is going to be orbiting in a way that's aligned with the orbits of the stars in the disk. Oftentimes you see active galaxies that are tipped over on their side relative to the disk. Sometimes you even observe systems, one of the famous maser disk systems is in fact counter-rotating compared to the direction of the galaxy. And so the point here is that there is no clear relation between the ionization cone orientation and the galaxy disk orientation. So that tells you that on those scales there isn't much sort of maintenance of alignment, whereas on these smaller scales, the degree of alignment is remarkably well maintained, which is quite interesting. Okay, so now I would like to discuss in some more detail the overall utility of the narrow line region, how the narrow line region is used to pursue all sorts of interesting and important studies beyond the important and interesting studies I've already covered. So what can you do with the narrow line region? Well, as I've already talked about when we talked about the broad line region, for example, the narrow line region lines are extremely useful for measuring systemic redshifts. Again, this table, which I showed you in detail and talked through in detail in the lecture on the broadline region, shows essentially the comparison between redshifts measured with various emission lines compared to calcium-2, which is a stellar absorption line that is thought to give a very good systemic redshift. And the point here I want to highlight is that if you look at the forbidden lines, like oxygen 3, even better oxygen 2 here, they can typically give you systemic redshifts good to sort of 45 to 65 kilometers per second. You have to be careful to take out luminosity effects. You can see the details in this paper as one example of many. But the point is that the narrow line region lines, being narrow, being very sharp and well defined in many cases, lets you, and being not generally offset too strongly from the systemic velocity, give you a very good way of getting systemic redshifts for active galactic nuclei. So they're just very practically useful in that respect. Also, I will mention in passing that they also are very useful for just flux calibration of spectra, because the narrow line region lines, if they do vary, they only vary very slowly over long time periods. And even then, the variation is generally quite moderate. And so you can, provided you're not looking over too long time scales, use the narrow line region lines as at least a first order flux calibrator of spectra. Another point of utility for the narrow line region is you can use it essentially as a bolometer to measure the total bolometric luminosity of an AGN. And that works even for obscured AGNs, owing to the fact that, as I've talked about, the narrow line region normally lies outside any small-scale nuclear obscuring material. And this can be appreciated from looking at these two plots down here, which show the O3 luminosity versus, in this case, the hard X-ray luminosity, which is another pretty good indicator of the bolometric power of an AGN. And the same thing is shown here of, again, O3 luminosity versus X-ray luminosity, with many more data points included now. And you can see that while there is surely scatter there in both cases, over orders of magnitude here, the NLR lines can be used pretty well to estimate rough bolometric luminosities. Again, even for obscured AGN systems where it can be otherwise hard to measure the true system power. So that's another very useful point about the narrow line region lines. They can tell you the power of AGNs, even obscured ones. Another very useful aspect of the NLR lines is that they can be used to identify AGNs using narrow line ratios. So this is often done with these diagnostic diagrams shown here, where people in these diagrams here, people have gone out and gotten large numbers of spectra, many thousands or even more spectra of galaxies. Some of these galaxies may contain obscured AGNs, other ones not. And the question then is, well, how do you identify among all these spectra that you have the ones that have AGNs in them? Well, you can utilize narrow line ratios to do that. The typical diagrams that are often utilized plot generally the O3 to H beta ratio, which serves as a pretty good indicator of ionization level, with high ionization levels up here being driven again by the fact that O3 is a high ionization line, and low ionization levels being down here. And then people along the other axis will plot a number of things. They often plot the ratio of, again, nitrogen 2 to H alpha, or sulfur 2 to H alpha, or O1 to H alpha. So in other words, you're looking at various ratios here. So O3 to H beta, for a system with only narrow lines like this one here, well, that's the O3, that's the H beta. Okay, so you look at that ratio. Or you look at, silicon 2 to H alpha, or nitrogen 2 to H alpha. And so you can see those here. There's the nitrogen 2, which is kind of blended with the H alpha, and the silicon 2, I believe, is over there. It's just off this particular plot. And then you can also look at the ratio of O1 to H alpha, okay, which is here compared to H alpha there. So you can look at those line ratios. You plot them in these characteristic diagrams, and you see where the various objects lie. And they generally follow a pattern where lots and lots of objects lie along here, and then there's this sort of tail of objects that go off in this general direction. Okay. These diagrams, by the way, are referred to as BPT diagrams, or Baldwin-Phillips-Turlovich diagrams, after the people who originally started utilizing these diagrams for these types of purposes. Although the studies have been well advanced over the years since then. And again, these characteristic line ratios, well, tell you a number of things. As I mentioned already, The O3 to H beta ratio distinguishes high ionization levels from low ionization levels. Similarly, whether you get O1 being strong compared to H alpha, so again, this one compared to that one, is significantly dependent on whether you have a significant amount of X-ray emission in the system. X-rays are required to penetrate deep into line-emitting material, line-emitting clouds, and the X-rays can penetrate deeply into these clouds and produce a significant amount of O1 emission, which otherwise is not easily produced. You have to go beyond the hydrogen ionization front to be able to do that. And so again, X-rays are over here, no X-rays are over there. And so what you find then is there's a bunch of objects over here. These are generally consistent with being ionized by young stars. They're labeled here as H2. Then high ionization systems that also have significant evidence for, again, X-ray emission. These are often classified as safer type objects up here, the higher ionization systems. And then you have lower ionization systems down here, the so-called low ionization nuclear emission regions, okay? And they can separate out, and people have derived detailed methods to distinguish when you have a liner versus when you have a safer galaxy. These are some characteristic separators discussed in this paper. With the basic idea being these are the systems that likely have higher accretion rates, higher Eddington ratios, and generally as you go down in this direction, you're going toward lower Eddington ratio systems. But all of these things over here in general are thought to be AGN ionized, where the systems over here are ionized primarily by young stars. So again, just from the line ratios alone, you can pull out pretty effectively, not perfectly, but pretty effectively, which systems are likely to have AGNs in them. Okay, different separators have been derived. I believe, the red solid line here is a so-called extreme starburst classification system, and then this blue solid line is a more sort of empirical separator, which some people believe works better, although there's some debate on exactly those details. But the point, again, is that with narrow line ratios, you can separate out AGNs from your typical galaxies, which can, of course, greatly outnumber the AGNs. So this is another reason why these line ratios are useful. There are many complex details of all of these diagnostic diagrams. If you'd like to read some more about the atomic physics of these various line ratios, I will refer you to section 6.1.2 of the book by Netzer as one example. There's plenty of other discussions of this, as well as, of course, the papers such as this one, which present these types of diagrams and, derive optimal classification methods within them. Okay, so that's another point of utility for these NLR lines. And then another point of utility is that the narrow line region emission links to that eigenvector 1 quantity, which I introduced when we talked about the broad line region. Okay, and in fact, you can see that here. Here is that eigenvector 1 quantity, you will remember, which connects together emission from the broad line region and emission from the black hole region, measured here with X-rays, okay, and reaches all the way out to the narrow line region. So this is a set of nearby quasars, redshift less than a half quasars, and the fact that O3 links to eigenvector 1 is an immediate strong argument that at least much of this eigenvector behavior is not simply orientation of the system, that much of this behavior is indeed a fundamental property of quasars in general, indicating there's structure to these quasars, as I discussed in more detail in the lecture on the broadline region. And then again, the fact that at rather similar luminosity, as you can see, you can have a wide range in O3 luminosity. Well, that may be due to, again, the covering factor of the illuminated NLR gas changing with the Eddington ratio, such that as you dial up the Eddington ratio, which corresponds to this end of eigenvector 1, the strong iron 2 end. So over here, these systems have a structure on small scales that collimates the ionizing radiation and allows less of it to reach out to the narrow line region. That's the basic idea for why that is the favored interpretation, although there's still some uncertainty and debate there as to why the O3 gets very weak when you dial up the Eddington ratio. Okay, And then finally, in terms of these points of utility for the narrow line region, I want to highlight that we have additional uses for the narrow line region as well that I've already covered. As we've talked about, the NLR has this fascinating spatially resolved dynamics that tells us about AGN outflows, tells us about the environmental effects of AGNs, and I'm sure for those of you who saw the previous lecture on AGN winds, you were appreciating that there are connections here. Remember that in the previous lecture we talked about, for example, how people can trace large-scale molecular outflows from active galaxies using tasty things like carbon monoxide and hydrogen cyanide, and how you can see evidence for broad line profiles in carbon monoxide that trace giant molecular outflows with tremendous amounts of gas outflowing, and how you can also use integral field spectroscopy to see outflows, and these outflows may provide feedback to the interstellar medium. All of these ideas, I'm sure you can appreciate, are broadly connected to what people are similarly talking about for the narrow line region, where people see now their narrow line region often has an outflow character and may be related to this feedback phenomenon. And indeed, many of the people that do these sort of molecular outflow studies and similar are also the same types of people that have been studying the narrow line region for many years. And so there are substantial connections between the NLR and the large-scale molecular outflows discussed in the previous lecture. I will not go through all of them here, but you're certainly welcome to go back and re-review that material, and I'll leave sorting out all the connections, to the viewer as an exercise. Okay, and then, finally, in terms of utility, as we've already talked about in the case of ionization cones, for example, the anisotropic illumination also, of course, provides valuable clues about AGN geometry and orientation. You can see that there's a small-scale collimator of the ionizing radiation. You can see that collimator often lines up with the direction of the radio jet. So it gives you important clues about AGN geometry and orientation, which is quite nice. So, the NLR has a lot of very valuable uses. Again, getting redshifts, flux calibrating spectra, using it as a bolometer, using it to identify AGNs in large spectroscopic samples, using it to understand important AGN correlations spanning a wide range of scales, using it to study dynamics, and using it to understand dynamics and environmental effects, and then also giving us clues about AGN geometry and orientation. I mean, that's a heck of a lot that the NLR gives us. So it's very worth studying this in detail. Just to wrap up today then, I want to end with one other point, which I've alluded to once or twice before, but have never really talked about properly, and that is, why is there this breakdown of the line-emitting regions of AGNs generally into a broad line region and a narrow line region? Why are there two regions, especially for when you consider lines like H-alpha and H-beta, as I will discuss? An alternative could be that you would just have a single continuous region, at least for lines like these. And so why is there this breakdown into a BLR and an NLR? What's up with that? That's what I'd like to talk about now. What do I mean by that in more detail? Well, here you can see, if you look at H-beta, the profile of H-beta here has this broad component to it down here, and then it has this little spike sticking up, which is very kinematically distinct from the broad component. You can see there's two distinct components, and you can decompose the full line emission into a broad component and a narrow component. And the narrow component has dynamics that are of H-beta, which is, again, is a recombination line, has dynamics that are rather similar to those of O3. Okay, so why is that? Why do you have these two distinct line-emitting regions that kinematically break down into a broad lump with a spike on top? Okay, and the similar thing is seen here for H-alpha. Why is that? Well, that's a good question. Now, one can understand that straightforwardly for something like oxygen 3, because remember, oxygen 3 being a forbidden line is collisionally suppressed on the very small scales. And so it's not surprising that you don't get much O3 emission from very small scales, and that's going to be kinematically distinct simply because it's a forbidden line. So it can only be made when the density is low enough that you can get substantial forbidden line emission. And that applies generally for all these forbidden lines. So that's really not what I'm focusing on here. Instead, I'm focusing perhaps more on, again, the recombination lines. Here you can see the radial dependence expected for H alpha here, with this dotted curve, and then for H beta here with this other dotted curve. And you can see the radial dependence of those is much less because, again, they're recombination lines that don't suffer from this collisional suppression effect. So what's up with that? Why do those break down into a broad component and a narrow component? That's a good question. This basic decomposition of lines like H alpha and H beta is seen over a large range of AGN luminosity, over a large range of redshift, over a large range of Eddington ratio, over a large range of spectral energy distribution. What's going on? Well, the fact that it exists over all these parameters suggests that there's some basic physical process at work here. And I want to talk about that briefly. However, just in passing, I do want to mention that, to be fair, there is a significant literature on a so-called intermediate line region. I will not go into the details of that. You can read the literature about that if you're interested, although I would, at least from my reading of that literature, I don't find that somehow overthrows the basic decomposition of lines into a BLR and an NLR. Okay, again, that's a technical point which you can learn about more by checking the literature if you're interested. But overall, this decomposition seems to hold. Here's a nice example. What's up with that? Well, the thinking there is that basic decomposition arises due to the effect of dust. And you can see that in these nice plots here, which show the line equivalent width going out in radius. Okay, and the point being that you'll see that if you look at these lines, which have been calculated for different parameters about metallicity and ionizing continuum shape and so on, the point is that as you go out in radius, you come to a point where suddenly dust is able to form. And that is marked in each one of these panels by these vertical dashed lines. And as soon as dust can form, as we've already talked about, the dust starts gobbling up much of the incident radiation. In fact, about 80% of it is re-radiated by dust in the infrared, 80% of the incident radiation. And again, you can see that here. The dust is the dominant. Once you can get dust there, it becomes the dominant emission source. And so the point is that on small scales, where dust cannot survive, you get efficient production of line emission. And then you get out to a scale where suddenly dust can form, and the emissivity of the gas crashes down dramatically. Okay, and you can see that's broadly true for all of these lines. And, this paper has additional examples of that. And so the point is, once you get beyond the dust sublimation radius, which again are shown as the vertical dashed lines, suddenly dust can form. And at that point, the line emissivity of the gas drops sharply. And so then to pick up enough additional mass that you can get a substantial amount of line emission, you have to go out fairly far to accumulate a sufficient volume, a sufficient mass of gas that you can actually get a decent amount of line power from the dramatically reduced emissivity gas. And so that's the basic point here. The formation of dust is thought to be the basic idea that leads to this BLR plus NLR decomposition of AGN spectra. And you can read more about that in this original paper by Netzer and Leor back from 1993 that discussed this type of idea in more detail. But that's likely the cause of the distinct BLR plus NLR structure present in AGN spectra. It's the formation of dust, and that causes the emissivity to crash down, and you have to go out to a much larger distance for lines like H alpha and H beta, which again don't have this collisional suppression, where again you have to go out to much larger distances before you can pick up enough line power, before you can get a decent amount of emission. And so again, this broad lump here is coming from a small mass of high emissivity gas, and this spike is coming from a large mass of low emissivity gas, and that is what causes this breakdown. Okay, so with that, I will come to an end, although today I would like to give one acknowledgement, because I personally don't actively do research in the narrow line region. I find it all very interesting, but there's only so many hours in the day, and so Ari Leor very kindly gave me helpful, constructive feedback on this lecture and suggested many valuable additions. Okay, so with that, I will end, and thank you.